Based on that, we'll be seeing this parallelism will work, right? So here, here two statements, Si and Sj can be executed in parallel, denoted by Si, two pipe symbols I use, and Sj. Parallel execution it is. Parallel. How do you denote? Si parallelly executes what? Sj. So for us now, Si and Sj are representing what? Set of input statements and set of output statements. Okay, and how do you manage them? Now let's see. If one condition, input statements of S, input statements of S of I, or S of what do you say, J, you can have output statements of S of I. This is S of J. Or else I'll write the condition in paintbrush so that I can draw quickly. I can say refer to conditions of Bernstein's .png file. Better, so that we can mention all the things of what we need in it. So .png file, and what it is, let's see. We'll open paintbrush image and we'll see there what actually happens. So I'll open paintbrush. Okay. Now I'll write all the conditions so that we can represent easily. Here I'll write if I of, I'll increase the font size. If I of S J output of S of I provides O of S of I provides O of S of J. This is one more condition. This here it starts, here it ends. One more condition. Again, provides all execution of I of S of I then again output of S of j, S of j, close. Three conditions are there. Okay, now we will draw all those symbols that will explain the total condition, right? So let's denote how this Bernstein's condition will work. This is one symbol we have, which will show us the importance of this inter. Okay, and the second thing we require to represent this pi symbol. This is one more representation. Now, these all, whichever the variables we have, they will be like subscripts to j, S of j. This I also represents subscript to I. This I also represents subscript to S of I. This j also, this j also represents script to j. Subscripts to j. And this I also represents subscript to this set of statements. And this j also represents subscript to I. These are our set of statements. So let's see how process will go now. And here we have this to be with intersecting with the code, with the condition. Either you have to execute all those things connecting with this statement, or all those statements need to be executed by this. I can just mention here as Bernstein's conditions. Bernstein's condition with what? Three, what do you call, flow of statements, three flow. So that if it satisfies all, then only we go with further implementations of it. Right? So now what do you say? That these are all conditions, or you can even describe them here itself. Here itself you can describe. Three conditions are there. Three independent process will be explained here of these three. This makes one condition. This makes another condition. And this makes third condition. Okay, three conditions. And on what basis they will specify the condition? That actually goes with what? Three execution process. And what are those three cases? What are those three cases? First one, Set of input statements provided with the execution of writing all these statements for output, that which you call as flow independence. We'll take mathematical expression and understand so that you can find actual importance of it. Output independence, and there is something called anti-independence. On the basis of these three only, your Bernstein conditions are going to provide their parallel execution of what process, right? And now, what are all these things refers to? That's what I said. The above listed conditions are called Bernstein's conditions and can be sent at different levels of granularity. For example, you can assume, what S may be, something like you can call machine level of operations. You can call machine level operations, or you can call as machine instructions. Anything you can refer. Now, how do you describe? You can say, in general, a set of statements that is nothing but called processes, or you can call set of statements, or what do you call set of processes, right? Set of what I said, statements, which may be related to what machine level operations, or you can call machine instructions. And what does it mean? Set of statements. What are they? Processes. How do you denote them? S1, S2, Sn can execute what in parallel. Provided what is the rule? If Bernstein's okay, so what did I say? Sn can execute what? Can execute in parallel if Bernstein's conditions are satisfied. Above conditions are there, on pairwise basis. Okay. Now, how do you proceed? So now you can say properties of parallelism or operator. First, what do you want? Si parallelly executes Sj, then it implies to Sj parallelly executed to Si. And what is this called? This is commutative property. This is one parallelism property. That is. Whereas in terms, if it is one more, if it is not transitive, then Si parallelly executed to Sj, Sj, and Sj parallelly executes Sk does not imply what? What it does not imply if it is not transitive. Si parallel execution. That is what? Sk. And what is this called? These dependencies are usually portrayed what? In the form of called data dependence. This is a directed graph having as many nodes as there are procedures or statements depending upon the granularity of the data dependence analysis. I said now we'll analyze predictions through this what do you call X, right? So that with mathematical expression you can easily understand what it means called flow dependent, output dependent, anti-dependent. We'll see that through softball example. Let's assume in example 1 S1. This is one expression in first expression. A assigns to x plus b. This is my one mathematical expression. In S2, I'll write C assigns to A multiplied by 3. I'll write. So now I can say S2 is what? Flow dependent. Flow dependent. On what? S1. Okay. And what do you see on S1? Indicated by an arrow directed from S1 to S2. This is one example. And what is important here is flow dependent. In execution of first expression only, you can have its value to be utilized for second expression. S1, A assigns to x plus b, first expression. S2 assigns to A assigns to 3. And what here you find is S2 is output dependent. Why? Because after getting the output of the first expression, then it is being provided to what? First one, S1, indicated by an arrow directed from S1 to S2 with a small circle anywhere on the arrow. This is example for output dependent. Let's see what is B assigns to A plus 3, S2 A assigns to 3. Now you can say S2 is anti-dependent on S1, indicated by what? An arrow directed from S1 to S2 with a small line across the arrow. Small line across the arrow. Now, some other important is compilers can actually use constraints condition to generate parallel code from sequential programs. However, this approach is not what I said efficient, because why it is not efficient? The reason could be because it is not going to expose something called hidden parallelism, and it is always exploited in the reconstruction of operations. Do you understand? Based on this data dependence only, you can even find that we have even other things to examine for the above specified conditions. So why I said like they are not, why this is not? Because it cannot expose the hidden parallelism that is usually exploited by what? Structuring of what? Operations. However, this approach. And again, one more important thing that you find is, in addition to this data dependence, we have to examine two other dependencies called resource and control dependencies. Dependencies. First, we'll see what is resource independence. Independence. Here you can say resource dependence between two statements if they need the same resource for execution, right? Same. And one more is there that you can call as control independence. Here I can say if execution of statement S2 depends on some condition tested in statement S1, then S2 is set to be control dependent on S1. Okay, this is how you can find the things that which are made available for your Bernstein's condition. And one more thing, in this operating system related to important areas, especially for the sequential process, the two most followed conditions is one is precedence graph and the other is something called as Bernstein's condition. Based on that condition only, we can have something related to analyzation of how the execution process will happen between different expressions that are provided with what sequence of execution, how variables of one expression are dependent in another expression. Now, connecting with this process only, we'll be discussing something important again is the time dependency concept. See, those expressions, those mathematical expressions, these all things you should be clear to go with further problems that which are connecting with. Okay, so now let's see what exactly we have connecting with these all things, time dependency and critical code section. These are the two things that which are connecting with the other points that which are related to what the above two topics. Right. Let's understand what exactly the point is. Okay. First one, time dependency. In that, we'll discuss what is mutual exclusion problem and critical code section. Dependency, then mutual exclusion problem, and then we have critical code section. Three things. We'll see all the things step by step how this we are going to achieve. Right? Now let's assume like consider that consider a system containing what set of processes consisting of n. So what are those processes? Denote them. A process that which is say for example P0, process 0, process 1, process 2, so on, process n. Then you can, each process has a segment of code called critical section. Critical section, in which what will happen? The process may be changing common variables, comma, updating a table, then something writing to a file, and so on. And the important thing that you find is, the important feature of the system is that when one process is executing in critical section, then no other process is to be allowed to execute in critical section. Then what do you say? Does the execution of, what do you say? Execution of what? Critical section by the process is mutually exclusive in what now? Time. It means what? When one process is getting executed in critical section, no other process will be allowed to enter into what now? That critical section until it does not complete its what? Task. And what do you call? You call mutually exclusive in what? Time. The execution of critical sections you can define like this. Critical sections by the process is mutually exclusive time. And what is the other thing, important thing is, each process whichever want to get executed now, it should take permission. Each process must request permission to enter into critical section. And the other important thing that you find is, the section of code implementing this request in the entry section. And what do you find? Even that once the process is done in your critical section, the critical section may be followed by what? An exit section. An exit section. And whatever the remote is there now, that code The remaining code is the remainder section. Remainder section. And now the point that you find, especially to this critical section, you can list out, I say, a solution to the critical section problem must satisfy what it should satisfy. Three requirements. What three requirements? One which you call as mutual exclusion. Do you understand? That is one point we have. Mutual exclusion. And what will happen at mutual exclusion problem? Mutual exclusion. I can say if process P1 is executing in critical section, then no other process can be executing in that, again, what critical section, in the same, I mean to say, it should complete it, exit from there, then only it can enter, it will allow you to enter into what the second process can be executed. Among the above three requirements, this is one more requirement that we call as progress. If no process is executing in critical section and there exists some process that wish to enter the critical section, then only those processes that executing in remainder section can participate in the decision of which next process can enter into critical section. This is second point. What actually the two different things is? Mutual exclusion is what? When one process is in critical section, no other process can be executed or cannot be executed in that same critical section again. And what about the progress part? What is the other requirement of this critical section? Then I said progress part is if no process is executing in the critical section, and if there exists some other process, then if it is interested or if it is wishing to enter into this critical section, so who should decide now? Remainder section. It is decided on the basis of what? Remainder section. Remainder section will decide what is the next process that can enter into what? Critical section. And there is something again called bounded waiting. This is one more thing that which can overcome the problem of what? Critical section. And here what will happen? There exists on the number of times a bound on the number of times that other processes are allowed to enter their critical section. After a process has made a request to enter its critical section, and before before that request is granted. That is about bounded waiting. Right? And these are our three what that will overcome the problem of what? Critical section. And on the basis of this only, we have different algorithms that have been introduced. That in deadlock handling, all those things that which are connected. Okay, so we'll see all the things that which are connecting to this. With the mutual exposure problem, we have something related with the different solutions that are introduced for this concept. These all things are there, and in continuation of this only, we'll be discussing about what is inter-process communication, what is deadlock handling, and all those things. This is one part of this critical section is that we have tried to come up with its introduction. Okay, so we'll stop the session here. Tomorrow I'll continue with the remaining things that which are connected with the same topic: time dependency, mutual exclusion problem, and critical code section. And in that only, we will try to come up with things related with the what deadlock handling as well as inter-process communication. Okay, those things we'll be discussing. And even we have different mechanisms or different techniques to handle things related to what? Deadlock handling. So those things also